So we saw how you could determine the convergence or divergence of a geometric series simply by looking at that common ratio. So let's look at an example. So here we have a geometric series, and I've intentionally not written it in standard form because I want to show you how it's easy to tell if it's geometric, even if it doesn't look like the typical geometric. First of all, let's just write out the first few terms here. So starting with n equal 2, we've got 3 to the 0 over 4 to the 1. And then every time n goes up by 1, that minus 2 or minus 1 just affects the starting position. It's just going to go up by 1 each time. Right now, the next time when n's 3, that's going to be 3 to the first, 4 squared, then 3 to the second, 4 cubed, and so on. The thing to notice is that as we go from this term to this one to this one, it goes up by 1 degree in the 3 and 1 degree in the 4. So it doesn't really matter that they're different degrees. It's that this is times 3/4 times 3/4 times 3/4. So we can see easily from here that our r is 3/4. Remember, another way you could do it is to write this term over this one, third term over the second, and so on. They should all give you that common ratio. But to go from there to there, you multiply by 3/4, multiply by 3/4, and so on. So we see that we've got, in this case, remember we describe a geometric by two values. It's a and it's r. A is where it starts. That first term, 3 to the 0 is 1, 4 to the 1 is 4. So the first term is a fourth. And the common ratio, the thing you multiply by each time, is 3/4. And this tells us that it's a convergent series, convergent geometric, because its absolute value is less than 1. So the way I'd like you to say this when you make your argument is to say that the series (3 to the n minus 2 over 4 to the n minus 1) converges as a convergent geometric, we could say. That shows me you understand that it's a geometric series, and that the key is that the absolute value of r is less than 1. And we can go a step further. Remember, with geometrics, not only can we say they converge, if r is less than 1 in absolute value, we know what it converges to. We know that the series actually equals a over 1 minus r. So a over 1 minus r. So that's 1/4 over 1/4, or 1. So convergent geometric. And I want to see all of this in your argument. I really want you to restate the series right before you say convergent, because later on our tests are going to involve multiple series, sometimes some limits of sequences, and there's lots of convergence and divergence going on in the argument, and it's best to be specific. So avoid pronouns, avoid saying it converges. Say specifically what you're talking about there. So that series converges because it's geometric, absolute value of r. This shows me you know what r is there, in case you hadn't stated it already. And typically, we'll also find the sum for geometric since we can. But that's it. Geometric are some of our easier series to do. Now, let's look at how we could maybe spot that this is geometric without even writing out some terms. It doesn't look like a to the a times r to the n minus 1, like the standard, I wrote this before. It doesn't quite look like that, right? So I can't just look at that and figure out what a and r are. But if I just think about what do the terms do without even writing them out, every time n goes up by 1, that power goes up by 1, and that power goes up by 1, and that's it, right? That's the only change. So each term is the same as the previous term, except for now you've multiplied by a 3 on top and a 4 on bottom. So that is a geometric. That's what we're seeing here. So the way to spot one is, even if it's not quite like this, the only place n should appear is in the exponents, right? So you have, you don't have any n's. It's not times n or any other functions in there. It's just some numbers to the n. Then that's a good sign that you've got a geometric series. And if you're unsure, just list out a few terms and check the common ratio.